How are you? How are you?
Hello?
Can you hear me?
Yeah, I can hear you. What's up?
We kind of have our lesson today.
Yeah. Right. We're still on circular motion, eh?
Yes. What are we up to? I think we were on banked tracks.
I'm not sure. Oh, what was the last thing we did was the inclined plane question.
Yeah. Yes. Now we're on bank tracks.
Yeah, I think so.
Yeah. So are you happy with all that bank track stuff? Inclined plane questions?
Yeah, inclined plane, yeah. Maybe there's like one or two now and big done with it.
Okay, no problem. So you have to move on?
Yeah.
Perfect.
I'd love to come in person, but I come from school at like 4:20, and by the time I get changed, this, that, I think I'm gonna be like 20, 30 minutes late.
That's all right. Also, I have your next test at the end of class.
For what, projectile or?
Yeah, projector.
Oh.
So that will be the last half hour. Do you have any notifications for any upcoming tasks?
I don't have a notification for physics, no, but I got some for English.
Okay. As soon as you get one for physics, please send it across to me.
Yeah, I'll let you know. It's going to be, the teacher says it's going to be like prac and like written or something. I don't know. She's going to have like two groups doing something, something like that.
Yeah, my first task was a prac, and I had to do the experiment that we were talking about last lesson.
Yeah. Okay.
All right. Do you have the work up yet?
The circular motion. Let me just grab my pencil case.
No problem.
Yes, I'm all ready.
All right, cool. So we looked at inclined planes last lesson, just a nice recap of year 11. But one thing that is actually pretty cool is that they have an application to circular motion. So an example of that is like the velodrome in the Olympics for cycling.
Yeah.
Yeah. So what actually happens is they do that for a specific reason, and it's something that civil engineers do. So when they construct roads, they often bank the road, so they slant it at an angle. And the reason why they slant it at an angle is because, as we're going to find out, some very interesting things happen. So you remember back when we were talking about when an object or when a car turns around a circular bend, how the centripetal force is equal to the friction force?
Yep.
But remember, if a car is traveling around a bend, a car weighs quite a bit, so that's a lot of friction force acting on the car.
Yeah.
Because the friction force is going to be mv squared on r. So one thing that we can actually do is bank the road, and if we bank the road, we actually decrease the friction force that is acting on the car.
Hold on, sorry, can I have 1 second? Sorry.
No problem.
Yeah, sorry about that. I'm back.
So as I was saying, one reason why we bank the road is because it actually reduces the friction force acting on the car. Because we want a lower friction force because, well, that's just kind of how we are. We want things to be easy.
Yes.
So this is where banked tracks come in. So can you see the diagram on page 24?
On page 24. Yeah.
If you have a hard copy, yeah, it'll be page 24. So on that, that's essentially how a banked track works. But one thing that I like to point out, it's very different to regular inclined planes. Because on regular inclined planes, we were talking about forces that are perpendicular and parallel to the surface. Do you remember that?
Yes.
Now we're actually talking about whether it's straight up or straight across.
Okay.
Yeah. And there's a reason for that. And the reason for that is because the centripetal force acts towards the center. And the center of the circle is going to be across.
Yeah. Horizontal.
So this is an example of one without friction. And what we're going to do for question 1, in the same way that we calculated the, remember V for the conical pendulum?
How do we calculate V for the conical pendulum?
We have to resolve the vectors. So you remember how mg equaled t cos theta?
Oh, yeah, because the tension. Yeah, I remember.
And t sine theta equals mv. Yeah, so you're going to have to do the exact same thing. Well, not exact same, but a similar process for n sine theta, n sine theta, n cos theta, mg, and mv squared on r.
Okay. How come n sine theta is horizontal? I'm looking at the diagram now.
Well, do you remember how, what do you call it? The friction, the normal force always acts perpendicular.
Yeah.
So we're not actually doing the mg sine theta triangle anymore, but we can actually do the triangle with ends.
Oh, if the normal force. Okay.
Yeah.
There it is. Okay. Okay. Fair enough. So pretty much this is just to have less friction.
Yeah.
Okay, sweet. Did you want me to do question 1?
Yes, please.
Oh yeah, okay.
Yeah, that is deriving it.
Yeah, okay. Derive an expression for the velocity in terms of 10 result of forces on the bank track. Terms of G, okay. Normal force, yeah. Yeah.
Okay. Would you like me to show you?
Yeah, please.
It's very similar to what do you call it? Conical pendulums. So I will share my screen. Here we go. The idea is that, well, we can see that n cos theta is going to be equal to mg.
Yeah.
And we can also see that, well, Fc, the centripetal force, is going to be equal to n sine theta.
Yeah.
So when we equate them, that's just going to be n cos theta equals mg, and damn it, and n sine theta is going to be equal to mv squared on r. So thank you. So the hint that the question gives us is the tan, and tan is equal to sine on cos.
Yeah.
So all we have to do is just do, I don't know why this is happening. I have draw with touch on. All right. So then all we have to do is just do equation 2 divided by equation 1, because that's just going to be sine divided by cos. which is going to be tan.
Mhm.
So that means that the ends are going to cancel out. And I hope this looks familiar. Okay, I'm kind of mad at the moment.
Maybe you're touching the thing on the right.
I probably am, in all honesty, but it shouldn't be happening. Okay, and then from there, v squared is going to equal to gr tan theta. So v is going to equal gr tan theta. Does that equation look familiar?
No.
It should, because this is the v that we got for conical pendulums.
Is that the same thing? Okay.
Yeah, it's the exact same.
Maybe it wouldn't be bad to touch over that conical pendulum thing again.
All right, we'll just go up and we'll look at that. So for the conical pendulum, it works very similarly to bank tracks, but they're pretty similar. So we can clearly see that f cos theta is going to be equal to mg, and f sine theta is going to be equal to mv squared on r, because it's towards the center.
mv squared. Oh, because that's the formula for the centrifugal force. Yep.
Yes.
Yep.
Okay. So that means that, well, we've already done question 1, so I'll just do question 2. So that means that t cos theta is going to be equal to mg, and t sine theta is going to be equal to mv squared on r. If we divide them, so if we do 2 divided by 1, well, we're going to get tan theta is equal to v squared on gr. So v is just going to equal root gr tan theta.
Root gr tan theta. Okay. Because it's sine and cos. Yeah.
Yeah, so it works in the exact same way. So yeah, they're actually identical in method.
Yeah. Okay. Fair enough.
But so if we go to look at, so does this make what happened to it? So does that make sense how this one would work?
To the right, yeah. Because you got the centrifugal force and the vertical one.
Yeah, the normal.
Yeah, mg. Yeah.
All right, cool.
Divided.
So that was for the case where there's no friction. What about when there is friction?
When there is friction.
Because we know that we can have friction on inclined planes.
Yeah.
And that is on the next page. So as we can see, we have a friction force that is acting down the slope. So that means that the object will be going up the slope.
Yeah.
So what I'm going to do, I'm going to derive in front of you the friction down the slope, and then I want you to tell me what you get when friction is going up the slope.
Sorry, you were cutting out.
Okay, so I'm going to calculate the velocity when friction is going down the slope. So I'm going to do question 1 on page 26.
Yeah.
And then after that, you're going to do question 2.
Yeah, okay.
So for this one, I can see that mv squared on r is going to equal to n sine theta plus f cos theta and that, actually, no, it's incorrect to start off that way. I should have started off with net force y in the y direction is equal to n cos theta, because I changed my direction. N cos theta minus f sine theta minus mg. So therefore, mg is equal to n cos theta minus f sine theta. Does that make sense so far?
Where is the f sine theta coming from?
From here.
F sine theta. Oh, okay.
Yeah, and then this is also n cos theta.
Yeah. Okay.
Yeah. And then the second one is just going to be, well, in the x direction, that's going to be equal to n sine theta plus f cos theta minus mv squared on r. So therefore, mv squared on r is going to be equal to n sine theta plus f cos theta. Does that make sense so far?
Yes.
Okay. So these are my two equations. But this is where the complications start happening. So remember, we're trying to make V the subject. So I'm going to do, and I hope you're writing this down. I'm going to bring my work over here actually. I'm going to do 1 divided by 2. So what happens? Well, the m's are going to cancel. So that's going to be v squared on gr. Did you message me something?
No, it wasn't me.
Okay.
Your screen black for me. Like there's a grey square.
I thought I was sharing my screen.
No, oh, there it is.
Can you not see me share my screen?
Yeah, I can see your screen now.
Okay.
The grey square in the middle for some reason.
Okay, can you see this on the right-hand side where my mouse is?
Now I can, yeah.
Okay. So do you want me to go through this again?
No, I understood what you were saying. You just pretty much got all the things in the vertical direction from the friction once you resolved it, and from the normal force and the weight force. I get that. And X, the friction force, the centripetal, and the friction as well. Yeah, I get that.
Yeah.
Yeah.
No, that's wrong. And another thing that you might remember is that the friction force is equal to mu n. Do you remember that? So all those n's are going to cancel. So this is pretty lengthy. And that means that V is going to equal root, well, I should rather just do wow. Can you see that?
Yeah, I see.
Yeah. So I turned my camera on now because I was writing on my screen. But yeah, so we want V to be the subject. So we're going to do 1 divided by 2 and then rearrange for V.
Yeah. Okay.
So that is the velocity that something is going when friction is acting down the slope.
And so when you're acting down the slope, yeah?
Yeah.
Okay.
But if you aren't given mu, well, you might ask, well, how do I actually do it? Well, the equation v equals root gr tan theta is called the ideal speed.
Yeah.
So if v is great, so I'm going to put capital I. If v is greater than vi, you might want to add this to your note. So if the velocity is greater than the ideal velocity, then the object starts traveling up the slope. So there's friction down the slope. So this is what the formula is.
If the actual velocity is bigger than like velocity should be traveling at.
Yeah.
Yeah. It's going to be traveling up.
Yeah, so this is the actual number that it will be traveling. But how the theory works is that you remember when there's no friction, v equals root gr tan theta.
Yeah.
Okay. If v is greater than root gr tan theta, then it's going to start going up the slope. Which I hope makes sense, because if it's greater than the speed, it's going to go up.
Yeah.
And when it goes up, that's friction. Friction's now acting down the slope. So we get this formula.
Yeah. If it's going, yeah, I see.
Do you have all this written down?
I have, yes, most of it written down.
All right, I'll leave it up for you. And then after this, can you please do question 2?
Question 2, that's good. Draw an expression of velocity of the friction is acting up the slope. Okay,
Yeah.
so this is pretty much the opposite of what you did.
Yes.
Okay, so so
do you want a hint?
Sorry?
Do you want a hint?
Yeah, why not? You can always do it for a hint.
All right. Well, remember, if it's going in the other direction, it's just going to be like that, isn't it?
Yeah.
So the F cos and F sin are acting in opposite directions. So all you have to do is make that a plus and make it a minus.
Yeah, because it's acting up the slope, yeah.
Yeah. So this is a minus. So that means that, well, this is a minus. That is going to be a plus. So then therefore this is a minus and that is a plus.
Mm-hmm.
And that's it.
Well, that's pretty much it derived.
Yeah, that's literally it.
Yeah. Yeah, all you have to do is switch away the blue line, the friction, and then resolve that, and then there it is.
Yep, you just flip the pluses and minuses. That's it.
Yeah, that's it, right?
Yeah, but one thing I like to point out is that the blue happens when V is less than VI. So that means that the object starts falling down the slope. And when it falls down the slope, that means that there's going to be friction up the slope, hence the formula.
Yeah, okay.
Do you have any questions?
No, it's actually all right for now.
Okay. Did you have all this down?
Yeah.
All right, cool. Are you confident with attempting some questions in the concept check?
Yeah, I'll give it a shot. Why not?
All right, cool.
If centrifugal force is direct, like, do you want to start from 1?
Yes, please.
Okay. Why do you feel that you are thrown away from the center as the car goes around the curve? Inertia.
Yep. That's it.
Inertia, yeah.
So this concept is asking for the 3 subdot points. So the car going around the bend, on the rope, so the conical pendulum, and banked tracks.
And bank tracks, okay.
Yeah, so it's doing 4 things really.
Mm-hmm. Describe the forces acting on a car as it travels along a bend. Consider the road to have friction. Well, going around the bend, it sounds like a roundabout. Sort of like bend, yeah. So you'd have friction in the horizontal direction. You'd have that centrifugal force, which is Would I say that? No. I'd say that's the exact same thing as friction, yeah?
Yes.
Friction is the centrifugal force.
Yes. And why is friction the centripetal force?
Because it's a car driving on a road. There's no strings attached to the roundabout.
I need a little bit better than that.
Because it's like it's going in a curve. It's not linear. So I don't know. I don't know how to explain it properly, to be honest.
Well, if you draw a force diagram of the car, we have the weight force acting downwards.
Yeah.
We have the normal force acting upwards.
Mm-hmm.
And we have the centripetal force acting towards the center of the circle.
Yeah.
As well as the friction.
Yeah.
So what other force can the centripetal force be?
Nothing, just the friction.
Yeah. So the friction force is the only other horizontal force.
Yeah.
So it has to be the centripetal force.
Yeah. Well, there it is. What would happen to the motion of the car if there was no friction? Ooh, I know this one. It definitely drift. Yeah, that's literally the answer. If there's no centrifugal force, it'd drift.
Well, it wouldn't drift. It would just keep going straight.
Like tangential.
Yeah, because there's no friction, so there's no centripetal force, so there's no circle.
Yeah, that's right. Question 3. During the game of racquetball, a ball of 250 units swing with the string is 2 meters long and an angle for it. Draw a diagram in this idea. Okay. So the radius is 2 meters?
No.
No.
No. It's a conical pendulum. So this is the 2 meters. You're trying to find the radius.
Yeah. Oh, okay. So swinging freely in a horizontal circular path. Oh, when you say swinging, it has to be pendulum.
Yeah.
Okay. The string is draw a diagram. Okay, so you have the ceiling, you have the string, you have the angle, you have mg, you have the mass. The string is 2 meters. Calculate the radius of the ball's circular path. Okay, so x. I don't have the length all the way to the bottom, so I only have one side, but I have an angle actually. This is all right.
Yeah, you can use trigonometry.
Yeah. Right angle. Sine 42. So opposite on adjacent to sine 42 x equals, where's my calculator? 2 sine 42. 1.34.
Yep. So you're going to need that R because obviously, centripetal force has an R in it.
Yeah. Okay. Determine the magnitude of the net forces acting in the ball in this time. Okay, so we need to resolve. I think, yeah. Centrifugal. How do you say it again? I say it like a spastic, bro. Centrifugal.
Centripetal.
Centripetal.
Yes.
Centripetal. Okay.
So when it says the magnitude of the net forces, that's asking for the for the x and y.
Yeah. So I'd find the x and y, and then I'd find the resultant. Yeah. Or just keep them separate.
You keep them separate.
Keep them separate. Okay. So horizontally the centripetal, then vertically resolve that. Okay. Okay. What's the formula again? mv squared on g?
R.
mv squared on r.
Yeah. So we know that mv squared on r is going to equal t sine theta, and mg is going to equal t cos theta.
Mm-hmm. T, so we have right. Let's do the vertical direction first, right? So we have mg, so plus, so 0.250 times 9.8. That's minus 9.8. Acting vertically, we have t sine theta. T is m. Wait. What would t be? MV.
Well, you're going to find t in the next part D.
Oh, yeah. Okay. Well, I know the centripetal force is mv squared on r, and then when I resolve that, hold on, I can't resolve that, can I? That's just the horizontal thing, yeah.
That's going to equal t sine theta.
T sine theta.
Yeah. So what your line should be is just mv squared on r equals t sine theta, and mg equals t cos theta. I haven't asked you to sub anything in yet.
mv squared on r equals t sine theta, and
mg is t cos theta.
T cos theta. Okay.
And that's just the first step that we always do.
Yeah, the horizontal and the vertical. Yeah.
Yeah.
Okay.
So now you have to find t, and you can find t either through mv squared on r or mg. I recommend solving it through mg.
Yeah, because you already have everything. Yeah, 0.250 times minus 9.8 equals t cos 42. Divide that across. Minus 3.3. How can it be minus?
Oh, you must use minus 9.8.
Yeah, there it is.
But remember, when it's downwards, we've already compensated for that negative.
3.3 newtons. Okay. So now I have T.
Yep.
Yeah. I know that's easy. Just find the rest now. The horizontal force, 3.3 sine 42. And then that's the centripetal, whatever, the horizontal force. And then the vertical one is T cos theta, and that's it.
Mm-hmm.
Yeah?
Yep.
Oh, perfect.
Yep. Did you know the centripetal force is going to be T sine theta?
T sine theta, sorry, yeah.
Yeah.
Which is 2.21.
Yep.
Yep. Okay.
That's it.
That's it. So I just need to wrap my mind around this whole circular motion stuff. It's just like, you know what I mean? I don't know.
No problem.
I just need to get used to it. Okay. Calculate the, what's tensile?
You haven't already. Oh, wait. I thought you already done that.
Tensile force.
Are you on part D?
Yeah.
You've done that. You've done everything in C.
Yeah.
You can just leave it.
Hold on, but what is the meaning of the word tensile?
Tension.
I've actually never seen that before.
So you're calculating T, but you already calculated T.
Yeah, I have T.
I
don't know what
D and
oh
E.
my God, that's what it's calculating. Right. Calculate. Yeah, okay, we already have that as well. That's easy. Okay. 4. Consider a car traveling around the bend. The car is moving at 80 kilometers an hour around the curve of radius 250 meters. Calculation. Okay. In terms of m, okay, mv squared on r equals fc. fc equals, we don't have the mass. Hold on, how can I solve it in terms of m if I don't even have the force? I have two unknowns.
Well, the question is asking for in terms of m. So you just treat m like a number.
Yeah, okay.
Everything will work out, trust me.
Okay. mv squared 22.2 squared on r 350. 492.84 m on 3. Oh, I see what you mean. And so divided by 350, 1.41 m.
Yep.
Yeah. Perfect. Calculate the coefficient of friction the car is experiencing on the road at this time. So 1.4. So 1.41 m.
And that's equal to friction force.
Yeah, that's right. And
What's the formula for friction force?
Normal force times nu, yeah?
Yeah, and what's the normal force?
mg.
Yeah, they're your m's. They cancel.
That's smart. That's very smart. 1.41 m equals mg mu, and then you divide that. Okay. Beautiful. G mu over the hill. You write that. G is 9.8. Mu equals 1.41 on 9.8. 1.41. That equals 0.14. I don't know.
Yeah, you got it.
Can I skip? Like, how many decimal places? Just 2?
Well, the question had 2 sig figs, so 2 decimal places, yeah.
Yeah, sweet. A conical pendulum is set up. The mass of a suspended object is...
Don't do question 5. We might have to leave some for homework.
Yeah, okay.
Do question...
7 looks nice.
No, not 7. Do question 9.
9? Okay. A car goes around the banked corner at such a speed that there is no resultant frictional forces up and down the slope.
Yeah, so no friction.
No friction. Hold on, and there's no centrifugal force.
No, there still is a centripetal force.
But there's no friction.
No, you remember the first example without friction?
No.
You don't remember?
No.
Go up to page 24.
Page 24. Yeah. Oh,
So
and that's the second. Oh, yeah, I see. Sorry.
yeah, that's right.
Okay. The corners are radius of. Okay, so on the diagram, draw and label the 2 forces acting on the car. Right, so that centrifugal force, whatever, N and mg.
Yeah, so your diagram should look just like the one on page 24.
The one on page 24. Yes, that's right.
Cool.
Calculate the magnitude of the reaction force.
Do you know what the reaction force is?
N?
Yeah.
Yeah. So just resolve n sine theta and n cos theta.
No. You have to find what n is.
Yeah, that would be. What would that be? And well, mg will cos theta.
Do the vertical one. The vertical one works out more nicely.
The vertical one.
Mm-hmm.
Took the mass of the car, and the angle is 7 degrees. The mass of the car, okay, 1200 times 9.8, 11760. We have mg, right? And then mg cos theta. One 1672.3.
No.
No, because I found mg, and you go, isn't it mg cos theta?
Mg divided by cos theta.
Mg divided by cos theta.
Yeah, go back to page 24 and look at the diagram. We're no longer dealing with mg cos theta. We're dealing with n cos theta.
Yeah.
So n cos theta equals mg.
Mm-hmm.
So n is going to equal mg divided by cos theta.
Just n.
Yeah.
Divided by cos theta.
Yeah. So yeah, n equals mg on cos theta.
Cos. Okay. Hold on, but why is that?
I'll quickly show you. Here we go. Well, it's just based on the idea that, well, these two forces are going to be equal to each other, aren't they?
Yeah, n cos theta. Yeah. Oops.
Yeah, it's pretty straightforward.
Yeah. N cos theta. Yeah, that's right. Oops. Okay. See, calculate the magnitude of the centripetal force on the car. That's the one acting down the slope. So that's just
No, it's acting towards the center. We're no longer dealing with up or down the slope.
towards the center. So it's just n sine theta. Yeah. And then we have n as whatever the hell it was. I have to enter in my calculator. Sine 7. Answer times sine 7. 1443.95.
Give me 1 second. Yep.
Perfect. Perfect. Okay. Question. What question are we going to do now?
That's it. Do you want to do any more questions, or do you want to leave these for homework and move on?
I don't know. I think I'll do one more question just to get more comfortable with this.
All right. Do you want to do a bank track question or another question?
Honestly, don't mind anything.
Okay, you can do question 10 if you want.
Question 10. Suppose you want to negotiate a curve with a radius of 50 meters and a 15. If the coefficient of friction between your tires is apparently 0.50, then what is the maximum speed you can safely use? Oh, that's the VI business now, isn't it? I have that written down. I forgot what it was.
Look at it, but actually derive it in this question.
Actually, derive it in this question. This question came again.
Yeah. So I don't know what the end result's going to be, but I want you to actually derive it, because in the exam you're going to have to derive it.
I swear my teacher said you don't have to derive some stuff. I'm not sure what it was though.
No, look, in all honesty, I don't really care what your teacher says.
Yeah.
Because I've done the HSC. He teaches the HSC.
Yeah. Okay, that's fair enough. Okay. Right. So you're gonna find that thing again. What was it? With the friction. Oh, okay. So on the sum of the forces on the y direction.
So draw a diagram first to help you out.
Okay. And whatever the box, the car, whatever the hell it is. Angle is 15. Have mg cos theta, and sine theta. Then you have the friction. But no, where's the car going? Where's the car going to be going?
The car, well, you tell me. What way is friction traveling?
Well, if it's going up the slope, if it's going like, wait, no, down.
Is the friction going down or the car going down?
The car's going down and the friction's going up.
No.
Why?
Read the second sentence of the question.
If the coefficient of friction between your tires and the pavement is 50, down the slope. And that means the car's going up. There we go. Because I know actually in the opposite direction. I'm like, how am I supposed to know that? But it's in the question. Right. So in the vertical direction, we have n cos theta. I'll give myself some more space. Screw that. N cos theta. F sine theta and minus mg.
Yeah, I always recommend drawing a diagram.
Yeah, I drew. Thank God I saw the diagram, but without the diagram, I would have been able to remember. Right. Yeah, and then mg equals n cos theta minus f sine theta. Then some of the things on the and the x direction is n sine theta minus f cos theta. Is that it? N sine theta f. Am I forgetting? Oh, wait, that is the force. What am I missing from the x direction?
What do you? Well, say it again.
N sine theta and f cos theta.
Well, it should be n sine theta plus f cos theta equals mv squared on r.
mv squared on r. That's the, yeah, there it is. Okay, so now we have mv squared on r equals n sine theta plus f cos theta. Yeah.
Yep.
And then we have mg equals n cos theta minus f cos theta and f sine theta. Sorry.
Yeah. Yeah.
Okay, now I have those two, and I have to derive the formula in terms of what, tan and g.
Not tan. No, because we have friction, we aren't using the tan formula.
Yeah.
You want to make v the subject.
We want to make v the subject. Okay.
So divide the horizontal one by the vertical one.
Okay.
So just do a big fraction and put the horizontal one on top and the vertical one on the bottom.
Oh no, I have two equations. I don't know.
Yeah, you can do that.
Yeah, I was thinking because the way I will do this, I divide g across and I have m, and I just substitute whatever I got for m into the other
That
one.
will get super messy.
Yeah, I was looking, I'm like,
Yeah, trust me, you're gonna want to divide it.
Yeah.
Yeah.
But hold on. I saw the way, but it didn't 100% make sense to me. So I just get the whole thing, even though there's two equal signs, I just chuck it.
Yeah.
Okay.
So you have mv squared on r divided by mg.
Yeah.
And that's going to equal your n's and f's over your n's and f's.
I saw you do it that way, but how does that make sense, like mathematically? So, like, I don't know. Can you explain this to me?
Well, just like how we can, like, how we can add equations together and things like that.
Yeah.
We can also multiply equations and divide them.
Yeah.
So it's just something you can do. It's just one of the most common. Well, it's not really common in high school, but you can do it pretty easily.
I don't know. I've never had a question on this, man. I don't know.
Okay.
Okay.
Do you want to sub in M?
No, I don't want to sub in M. That's going to get really messy.
Okay.
This is obviously 100% a better way to do it. And here I like where you take out N and you have that, yeah. Right, whatever you do, just you want to make V the subject. Okay. Wow, I didn't know you could do that. Okay. Let's see.
So the M's will cancel.
The ends will cancel, yeah.
Yeah. So you have no more mass on your left-hand side, but on your right-hand side, the friction force is equal to mu n, remember?
The friction force is equal to mu n, yeah?
So all the M's will cancel on the right-hand side.
Oh, and I'll just be left with that. Oh, sorry, yeah, because I left mine in F. That's why I'm like, eh. But if I have M mu, then, yeah, that's right. All the ends would cancel, yes. And I'd be left with just that mu on the top and the bottom.
Mm-hmm.
Yeah?
Yeah.
And then I have sine theta on cos theta. Wait, no. Sine theta plus mu cos theta over cos theta minus mu sine theta.
Yep. And then all you have to do is multiply the GR over and square root the whole thing.
So right now I have V squared on GR.
Yeah.
And then multiply that across. And V. Hold on. Sine theta mu cos theta on cos theta mu sine theta. Right. And at this point, multiply that across. But hold on, man. I still have a fraction on the right side.
Yeah, that's fine.
I multiplied across, there's going to be on the numerator, and I still.
Yeah, so it's G. So you have the fraction, and GR is going to be on the top, and then you have the brackets sine theta minus mu cos theta, or whatever it is.
Yeah, but didn't Sean just have like 3 letters on it? That's why I was thinking I should cancel more stuff out.
No. It's only going to have 3 letters if there's no friction.
Oh, is that the one for no friction?
Yeah.
Oh, that's it. That's what confused me. Okay, I thought I'm like, how the hell am I supposed to cancel this stuff out?
Yeah, that's okay.
Okay.
But yeah, this one has friction, so we can't use that idea.
Yeah, okay, I see. This is easy then. The V squared equals GR sine theta plus mu cos theta all up on cos theta minus mu sine theta all in a square root. Yes. It makes a lot more sense when you do it yourself, sort of thing. You know what I mean?
Good. That's really good.
Obviously didn't do it by myself, but you get what I mean.
Yeah.
Okay. And now that we have that, I've no working out space.
Just sub it in. You just chuck it in your calculator and just sub it in.
Yeah. Fair enough. G 9.8. R. Do we have R? Yes, times 50. Bracket sine 15 plus mu. Where is mu? 0.50. Cos 15. Yes. And then we have cos 15 minus 0.40 sine 15. 20.85.
Yep.
Wow.
So this is how engineers in the real world actually determine what speed limits to go around what corners.
Wow. Is this it?
Yeah, that's literally the formula they use.
Oh, that's mad, bro.
Yeah. So they say, okay, the coefficient of friction of tar could be, I don't know, 0.3. I don't know this off the top of my head. Well, we're going to make it. We know when we're planning, we know what the radius is going to be. We know what the angle is going to be. Or if they're like, okay, we want it to be 60 kilometers per hour. We know it's going to be a radius of 50 meters. What angle is it going to be?
Then they figure all that stuff out. Yeah. Okay.
Yeah.
Fair enough.
So are you happy with bank tracks, conical pendulums, and cars in circular motion?
Now that I got this down, yeah, I'm happy.
Okay, because I'm being serious when I say this. Banked tracks was the second last question in my HSC.
Oh, so that means it's pretty hard, eh? If it's closer to the end.
It got pretty hard, yeah.
Oh, okay. Okay. Fair enough.
All right. Any questions before we move on?
Just summarize. So far, there's just 3 cases: the one on the string, the pendulum, and the car. Yeah, and the bank track. Sorry, 4.
Yeah. Well, technically there's 4 because there's the normal one where the car goes around the roundabout.
Yeah. Okay.
So there's
and plus we've got all the formulas at the start. I kind of forgot them, to be honest. I have to go over them. Well, I'll go over them in my own time, whatever. And yeah, now we're up to what? Energy and work.
Yeah. So this whole time we've been looking at horizontal circular motion. But once we get through this, we're going to actually be able to look at vertical circular motion. So like a yo-yo or like the bucket of water, those things.
Yeah. Okay.
But before we look at that, we must actually look at energy and work. So how much do you remember from module 2 about the types of energy and work?
Types of energy, we've got that gravitational, we've got kinetic, mechanical is the total, like the energy in the system that's left. Energy cannot be created and destroyed. What was that thing? Something work is equal to energy, something like that. Change
Change
work is equal to, is that the right, is equal to energy? Oh, okay. I see.
yeah, and work is equal to Fs cos theta.
Work equals to F cos. Oh yeah, I remember. Yeah.
Okay, so you might just want to kind of skim through this. You can either do it now or later, but I'm going to be kind of referring back to this when I talk about how this applies to circular motion on page 45.
Page 45. Okay.
Yeah.
Skim me through. Look, I don't know. I still remember this, to be completely honest with you.
Okay.
Okay, page 45. Yep. Yeah.
All right. So if anything is a little bit unclear or you can't remember, please read the prior notes.
Yeah, that's fine.
So firstly, let's talk about the kinetic energy. So we're talking about the horizontal circular motion, like the conical pendulum. So we know that the kinetic energy is going to be constant. Why is the kinetic energy going to be constant for an object in uniform circular motion?
In uniform circular motion, because it's uniform, there's no acceleration.
Well, actually, no, there is an acceleration.
Towards the middle, sorry, yeah.
Yeah.
Because it's always changing direction.
Yeah.
Yeah.
So why is kinetic energy constant?
Why is kinetic energy constant? Because you can't destroy it.
No, because in uniform circular motion, the speed is constant.
Oh, the speed is constant, yeah.
So kinetic energy is half mv squared. The m isn't changing and the v isn't changing.
Yeah, okay.
Even though the direction of v might change, we're not concerned with it. Okay. Also, with like a conical pendulum, there's also the gravitational potential energy, and that isn't going to really change for horizontal circular motion because, well, it's at the same height.
Yeah, okay.
So that means that for an object in horizontal circular motion, the energy doesn't change at all.
Yeah.
The kinetic energy is always constant, and the gravitational potential energy is always constant.
Yeah. Okay.
Also, for work. So in uniform circular motion, we are just going to look at work. So we know that F equals Fs cos theta.
Yeah.
But in uniform circular motion, well, we know that the force acts at right angles to the tangent, the velocity.
Yeah.
So therefore the angle is 90 degrees and the work done in uniform circular motion is 0. There's no work done in uniform circular motion.
Yeah, because it comes back to the start. Like this circle, yeah.
Yeah. So like if you ever get asked, oh, how much work was done in this conical pendulum, it's always a trick question. It's always going to be 0.
Yeah. Okay.
Yeah. So that's kind of how it works for horizontal vertical motion. But now we're going to be looking at vertical circular motion. Do you have that document?
Vertical circular motion, page 45.
Okay, so you have all the way to page 58?
When I printed, I think I printed everything.
What's the last page you have?
58, yeah.
Perfect. Okay, cool. So if we have vertical circular motion, which we can see in the image, I'm not going to do the little hand movements, but so I'd like to share my screen and I'll actually derive these with you. But the idea is, well, at this point, so for the blue point, the net force is going to be equal to mv squared on r minus mg. Can you tell me why it's going to be mv squared on r minus mg?
mv squared on r minus mg. So subtracting the weight force from the centrifugal force.
Yeah.
Force pulling it inwards because it's vertical, and because it's in a vertical, like talking about vertical circular motion, it's acting against gravity is acting against it.
Yeah. So basically all that means is, well, the centripetal force acts upwards and gravity acts downwards.
Yeah.
So could you tell me what the centripetal force would be at the top of the circle?
At the top of the circle?
Yeah. So at this point here.
The red one?
Yeah.
0.
Why?
Because that's probably the point where gravity fully cancels it out.
Not quite. So we have gravity always pointing downwards, but what way does the centripetal force point?
Towards the center.
Yeah, which is also downwards.
Yeah.
So it's going to be minus mg minus mv squared on r.
Oh, from the red point. Oh, yeah, okay. Okay.
Because both the forces are acting downwards.
Yeah, I see. Sorry. Yeah.
Do you have any questions about that?
No, that makes sense. Yeah.
All right, cool. So that was for an example where we have a ball or like a bucket for it. Oh, no, we'll go with the ball, like a ball on a rope, and we're swinging that around. But what about, and these are actually the most common questions that get asked about this topic, what about things such as loop-de-loops, like roller coasters or like Hot Wheel tracks? So if we're dealing with roller coasters and Hot Wheel tracks, well, then that actually means that, well, we have a normal force, don't we?
Yeah.
Because we're on the tracks.
Mm-hmm.
Okay. So remember, the normal force is always going to act in the opposite direction to, like, the normal force is always going to act to the center.
Yeah.
Because it's always going to be, well, at the top it's going to be pointing down because this is the track. And then at the bottom, it's going to be pointing up because this is the track.
Yeah, of course.
So we can kind of see this on page 46. So these are kind of the rules that you'll always employ when figuring out what forces go which way. So gravity will always be straight down. Normal force is going to be always towards the center. And the centripetal force is always going to be towards the center.
Yeah.
And tension as well.
Mm-hmm.
Tension's, because remember how tension is a centripetal force?
Yeah.
Yeah, so that's always going to be towards the center too.
Yeah, okay.
And one thing I would like to point out, because after this we actually start doing questions, is the centripetal force is always the net force.
The centripetal force is always the net force.
Yeah. So you're probably asking, what does that mean? Well, for the bottom case, it's going to be normal minus mg, but that is going to equal mv squared on r.
Oh, yeah, because it cancels out. Yeah.
Yeah. So the centripetal force is the net force, always.
Okay. Yep.
Yeah. So this is always going to be normal minus gravity or normal tension and gravity. It's going to be some combination. You have to figure that out yourself, but it's always going to equal to mv squared on r.
Yeah. Okay. Perfect.
Do you have any questions?
So far the theory sounds all right, to be honest.
Yeah, that's good. That means it makes sense.
Yeah. Well, if it's on the top though, actually, even in that case, it could still cancel out the normal force and the gravity. Yeah.
Yeah.
Okay. We're going to do the questions?
Yep.
Okay. A construction team is looking at building an exit ramp on the whatever freeway. They're concerned that cars should be.
Yeah, I guess, question 1 shouldn't be there.
Also, don't do question 1.
Question 1, yes. Question 1 should be for what do you call it? Banked traps, but I actually don't know how it got there. I must have left it there and forgot.
Yeah, it's fine. And question 2. A roller coaster is going for a loop that has a radius of 4.8 meters. Okay. The roller coaster cars have a speed of 13.8. Top of the loop. During testing and development of the roller coaster, it was determined that the cars and passengers have a combined mass of that much on an average run. Determine the amount of force the track was designed to in order to make sure the cars keep going around the loop. Okay, so I'm trying to find. This in. Okay, so it's just mv squared on r.
No, you're trying to find the normal.
The normal force.
Yeah, because that's how much force the track withstands.
But that's how much force the track withstands.
Yeah.
Oh, that's going the opposite direction of the track at the top.
Yeah.
Yeah. Okay.
So you must draw a diagram for these.
Okay, I see. I'll do the diagram. Q and down, mg, down. Wait, so if I'm just trying to find normal force, I just go mg.
No. You're always going to do centripetal force. So go back to the previous page.
Yeah.
Okay. We can see for the top, centripetal force equals mg plus n.
At the top, centripetal force equals mg plus n.
Yeah.
I don't see it. Where does it say that?
No, I'm looking at the diagram.
I'm looking at the diagram, okay. At the top of the circle, everything adds down. I see. Yeah.
So FC is going to equal mg plus n. You're trying to find what n is.
FC equals mg plus n.
Yeah.
Okay.
So mv squared on r equals mg plus n.
Then you just solve it. That's easy. But hold on, I got a question, right? If all three of them are acting in the downwards, yeah?
Yeah.
Yeah. How can mv squared equals mg plus n?
Well, we can see it through the diagram.
No, all of them acting in the same direction.
Yeah.
Yeah.
Well, let's actually look at it. If we this is I'm using blue. So if we were literally to add them together, we get FC.
If you add the normal force and the weight force.
Yeah.
How would that equal the centripetal force?
Well, because the net force is going to equal to mg plus n. but the net force is going to be acting downwards.
Yeah.
And that's going to equal mv squared on r.
I thought it was going to be mg plus n plus mv squared on r.
No, mg plus n equals mv squared on r.
Oh, because I thought all three forces are acting in the same direction. I'm like,
No. The mg and n are either going to add or subtract to give mv squared on r.
oh, okay, that makes sense.
Yeah.
Okay, that makes perfect sense. Yeah.
Yeah, because if we're acting in a circle, remember the net force is always going to be the centripetal force.
Mm-hmm. Yeah. Oh, okay, I see. The net force will always be okay. Okay. Do we have the mass? Yes. Times the velocity? Yes. Over the radius? Yes. Ooh. 4800 plus 0.8. Wait, how does this make sense? 0.14. That makes no sense.
Where'd you go?
0.14.
Nah.
Yeah, I was going to say, that makes no sense.
Remember, you're rearranging for n, so you would have mg plus n equals mv squared on r. So therefore, n is going to equal mv squared on r minus mg.
I'm so stupid, bro. I don't know why I divided mg across. I'm freaking blind, bro. Oh my god.
No, it's better that you're actually getting it and then making a dumb mistake rather than you actually going, I have no idea how to do this.
Yeah, I completely agree. 4,800 times 9.8. Right. But hold on, how is that? How did I get a minus number?
What'd you get?
Minus 40280.8.
No.
Yeah, so I'm like, what? Am I not plugging this in properly? 4800 times 13.8 squared on 9.8.
On 4.8.
I can't read my own damn writing, man. That's so embarrassing. 4800 times 9.8. 143400.
Yep. Yep. And now you're going to do the same thing at the bottom of the track.
B, determine the amount of force. Okay, so I know the centrifugal force would equal the net force. Okay, so mv squared on r equals to, at the bottom of the track, we are trying to find, and again, okay, mg plus n, 4,800 times 13.8 squared.
It's not going to be mg plus n.
So minus n.
No.
Wait, what? I don't know.
Go on the page 46 and look at the diagram.
Look at the diagram, okay? Fg is going downwards. So it's going to be mv squared on r.
Yeah, so mv squared on r, well, the net force is going to equal n minus mg.
Yeah, which is 0. N minus mg. Isn't n mg?
No. It's the same thing as the previous question. N minus mg equals mv squared on r.
N minus mg equals mv squared on r.
Yeah, it's just like how in the previous question, m plus mg equaled mv squared on r.
Hold on. In the previous question,
Yeah, in part A,
the gravity is acting downwards. Yes? The centrifugal force is acting downwards.
Mhm.
Yeah. The normal force would be acting downwards because it's pressed against, acting downwards because it's pressed against the track. Yes?
Yep.
In this one, we have of course, pointed to the center, the centrifugal force. We have the normal force reacting against being pressed against the trap, so that's acting toward upwards as well. And we have gravity acting downwards. So it would be minus mg. That makes perfect sense again. Okay. mv squared on r equals n minus mg. Okay.
Perfect.
There it is. 4,800 times 13.8 squared on 4.8 equals n, which is mg. Wait, what does n equal?
You're trying to find that.
N minus.
So n is going to equal mv squared on r plus mg.
Yeah, plus mg, yeah. 4,800 times 9.8. Okay. Two, 3, 7, 4, 8, 0.
Yeah.
Okay.
How are you finding these questions?
Look, dude, honestly, the concept's easy. I'm just not understanding how I'm not like I don't know. It's not too hard, man. I just need to I don't know. It's not too hard. If I keep practicing, it's gonna be easy. So it's all right. So yeah, I'm just gonna keep.
Let's do C, and then we're gonna have to do your speed test.
Speed test. All right. Determine the minimum speed the cars on this roller coaster can move in order to just barely make it through the loop at the top.
So do you know what that means?
Let me think about it for a second.
Okay.
So, we have the roller coaster and a circle, at the top. Okay. And the force going to the middle, normal force, and mg. Okay. What force is on to barely make it through the loop at the top? It's like, how fast does it need to go in order not to fall down from the top, essentially? Yeah? Okay, so we're going to leave V as a question mark. We have M. We have N as well. Oh, okay, oh, this is all right. 4,800 V squared on 4.8 equals N at the top of the track. Wait, that doesn't make sense what I'm doing. mv squared on r equals n plus mg. I mean, that's the formula at the top. mv squared on r equals mg plus n.
Yes.
Yeah.
But this is where the idea of minimum speed comes in. What the question is asking is, what is the minimum speed? But remember, the normal is dependent on the speed. So what happens?
If it's dependent, if the speed decreases, the normal force decreases as well.
Yeah. So what we're actually going to do is, well, this is how you tackle these problems. So I suggest note of this is when we're asked for the minimum, set the normal to greater than 0. So therefore, I'll write here, mv squared on r is going to typically equal to mg plus n, isn't it?
Yeah.
But if n is greater than 0, then all we have to write is mv squared on r is greater than mg.
Yeah.
And then solve for v.
MV squared on R is greater than MG.
Does that make sense? Because if we don't know what n is, but we know that n is greater than 0. So therefore, mg plus n is going to be greater than mg.
Yeah, I see. Oh, okay. Okay. I see. And then you just solve from there. Okay.
Yeah.
MV is greater than MG. That's all right. 4,800 V squared is greater than mg times 4.8 v squared. Hold on. When I square root, do I have to flip the inequality sign or not?
No.
No. That's only when you divide by a negative, yeah?
Yeah. Well, let's think about when I square root something. So 100 is greater than 25.
Yeah.
But if I square them, I get 10 is still greater than 5.
Mm-hmm.
So you don't change it.
Oh, okay. Fair enough. And v square root v. Wait, by the way, am I supposed to get a report now?
No.
Like from school?
No.
3. When am I supposed to get it?
You'll get one probably probably at the end of term 1.
At the end of term 1. Wow. Even for year 11. So I only have one report this whole year.
You haven't had one for year 11 yet.
I had one. When was it? End of term 2. I only had one for year 11. I'm supposed to have 2, like one after prelims.
Yeah, you should. I thought you were talking about your year 12 report.
No, bro. I was asking for the. I'm like, I still haven't got it. I don't know what's happening. That's why I was confused. So I'm supposed to get one, yeah?
Yeah.
This term?
Probably.
Yeah, okay. 4,800 times 9.8 times 4.8. 4,800. 6.86.
I got 7.2.
4,800 times 9.8 times 4.8 over 4,800.
Well, or you could just do v is greater than root 9.8 times 4.8. Oh, actually, let me double check. Okay, root 9.8 times 4.8. Oh, yeah, it comes out to yours.
Yeah, okay.
I think I typed 4.6. Okay. Oh,
That's happened to me many times, don't worry.
and that's it. Yeah. So we're gonna finish this inquiry question next lesson, more than likely.
Yeah. Okay.
And then after that, well, this is week 4 at the moment.
Week 3, I think, actually.
Oh, week 3. Okay. So that means that we'll probably finish this entire module probably by week 5.
Are you serious? What else do we have left to go?
We have talk, which is at the bottom of this booklet, and then at the end of this booklet, and then we have another inquiry question.
Oh, okay, fair enough. So there's pretty much 3 sections to this mechanics thing.
Yeah.
Okay, fair enough.
Yeah.
Okay.
I've sent you your speed test.
You sent me the speed test in the Skype chat or
email.
No.
Yeah. I just want to say one thing. So like I know that you'll be doing the speed test, but as soon as 7 o'clock hits, I'm going to have to go because I have another class.
Yeah, right, that's fine.
And then I'll give you the big one.
Sorry?
Oh, did you say something?
Yeah, I'm saying that I heard you talking.
Okay. But yeah, so if it hits 7, I'm gonna have to go. So I apologize about that.
Okay, no, that's fine. I was about to say, I'll try to finish quickly so we can
Go through the answers.
yeah.
No problem. So you can give yourself 25 minutes if you want, because I know that you finished a little bit earlier.
Yeah. How the hell do I print this, man? Unbelievable.
Oh, no, you don't have to print it. You just have to send me your work across. You just take a picture.
Yeah?
Yeah.
English physics series. Okay. Alright.
Yeah, when you're ready, you can begin.
Okay.
You got to make sure to time yourself, though.
Our time, so that's fine.
All right, go.
And you can just put the timer on. Oh, that's cool. Sorry.
I'll race you. I'll mute myself.
Sorry, I'm back. I was just talking to my dad.
No problem. I actually have to make the solutions as we go, so I'll actually end up racing you.
Yeah. Oh, okay. Sweet. I'll start the time now. Okay. Previous turn upwards from the top of the video.
Have you started?
Yeah, I've just started now. I'm reading the question. Previous turn upwards 24 degrees above the horizontal initial speed. U equals T equals 3. How high is the BB? Okay. Hold on, sorry. For the first question, I know it's exam, sorry, but for the first question, is it saying it's on top of the building, yet it's thrown up? Does that mean there's an arc at the top, or is it just going straight down?
There's an arc. It's type 3.
Type 3.
What question are you up to?
Just question 2.
Okay.
Yeah.
You know ramen?
Finished probably.
Nah, I'm on 3C.
3C? Oh, okay. Sorry, I'll be back in a sec. Sorry, I'm back.
Sorry, I realized that I was muted.
That's fine.
How are you currently faring?
I'm doing all right. I think so. I'm on 3B.
Cool.
Sorry, because I'm not familiar with tennis. What is the service line?
Oh, well, I wasn't either, but it kind of says it in the question. So when you serve the ball, you're 12 meters away from the net,
Yeah.
and service is half of that. So to be within service, the ball must be between 18 and 12 meters.
Has to be between 18 and 12 meters. Okay.
The last question takes a lot of setup.
Really? I'm gonna take a look at it. Do you want to send you my solutions now for question 3 up to 3B? Because I've got 3, 3, and 4 to do.
Yep.
I sent it to you so far.
Do you want them now?
Huh?
Do you want them now or later on?
Send them whatever in the group chat. I want to look at them. I'll send you my ones as well.
Okay.
What I have so far. Alright, I set up the 3B to you. Have a look at it and just tell me which ones are wrong.
Second question 1. Yeah, question 1's right. Question 2.
Question 2 I did on the page after page. Question
Yeah.
1.
Question 2, A is right. Good.
Yeah.
B is that 40.54?
To be honest, I can't read my own writing. I want to put 150.
I think it is because that's the exact same I got.
Yeah, that's the one. 40.
So that would be right.
Yeah.
What about part 3? Part 3 is right, but I can only give you 1 out of 2.
For the velocity.
You know why?
Nope.
Because velocity, direction.
Oh, the direction.
You need the angle.
Yeah. Sorry, I need to write that. Yeah. Okay. I know for next time. 1 out of 2.
So you're on 5 out of 6.
I lost 1 mark so far on 2C.
Yep.
Yep.
3A, what did you get for A? What did I get for A? For A, I got...
We'll pass over.
I'll give you 1.
Really? What did I do wrong?
You weren't meant to find Y, you were meant to find X.
But it gives me X, 12.
No. You're meant to find where the ball lands.
I thought I was just supposed to find if it passes over.
Yeah.
Yeah, so if it passes over, so I don't know. Like, did you get that it will pass over?
Yeah.
Yeah. But I don't, like, the way I solved it, I don't understand what's wrong with it. Like, I got the time, and at the time and that it reaches 12 meters horizontally, the height is 1.12, which is higher than 0.91.
Mm-hmm.
You know what I'm saying?
Yeah.
So at the point that it gets 12 meters horizontally, it is 1.12, which is higher than 0.91, therefore it will pass over.
Okay, I see your reasoning.
Yeah.
Like,
you know what I'm saying? I don't know, it seems logical to me.
I can see why you didn't get it. Well, not why you didn't get it. Your reasoning's right. It's just maybe the question is wrong. So I'll give you 2.
2? Okay.
Yeah.
But well, actually, you probably, yeah, okay, don't worry. Okay.
I'll send it to you and you'll see.
Yeah, okay.
For part B, I got, what did you get? I got the same as you. Yep.
Tick. All right, now up to 3C.
Yeah. So at the moment, you've only lost 1 mark. That's awesome.
Yeah, it's pretty good, eh? Because I did some of the practice questions and all that stuff. Yeah. So we go 3C. If instead Novak serves the ball. Actually, what time is it? You got to go?
I got a couple of minutes.
Yeah, okay. If Novak serves the ball 5 degrees below the horizontal, does this ace still occur? So you pretty much got to redo the question. Theta equals 5 degrees. So ux equals 3.2.
6 plus 5 degrees.
Hopefully, I will be like this circular motion. Just practice. That's all I need.
Yep. X, Y, K. Have change in X, Y, Z. So here I've got to prove that it goes over the net first, and then if it stays within the limit.
Yeah.
Yep. Okay. Let's see this. 5 degrees to horizontal. I've got it will pass over the net. Now I have to second part.
I didn't have that.
You didn't have that.
I had the ball hit the net.
You had the ball hit the net. Okay. All right. Let's see.
You know what?
Mm.
I'm going to take the last question out of the exam.
Why?
I have trouble solving it.
Is it just something insane?
No, just a lot of algebra.
Oh, really?
And you need to know something that I didn't realize that you needed to know.
Okay. Okay.
So I'll take it out.
4's gone. All right.
Yeah, so this one will be out of 14.
Okay. Yeah.
All right, I'm gonna have to go now.
Yeah. Okay. That's fine, man.
I sent you my solutions.
Oh, okay. Sweet. Thanks, bro.
If you have any questions, please message me.
No worries, mate. Thanks for your time.
No problem. Bye.